This presentation is delivered by the Stanford Center for Professional Development.
I have a one handout for you today. I expected to have two, but we had photocopier drama this morning, so I haven't photocopied your assignment yet. I'll post it as a handout after class today. You have plenty of time to do that. I'm not going to make this due until 2 Mondays from now. So it's not like you're in an immediate rush to get started on it, so that's why I wasn't stressing about it. But nonetheless, the assignment will formally go out today, and you'll have 2 weekends to do it. It's actually not too bad. It certainly involves some of the new threading stuff. You're revisiting assignment 4. You're implanting some thread directives to make a lot of stuff that was running sequentially before, and you felt the pain of that sequential execution before. Make it so that lots of things run in parallel, and things run really, really quickly, really, really beautifully. It's very impressive. It's a good end result once you actually get that thing up and coded. When I left you on Wednesday, you were all stressed because you had a midterm in 7 hours. But I was just getting through the dining philosopher's example. Let me review the picture. The idea is that there is food, big plate of spaghetti, at the center of a table, and there are, I'll be less caricature about it this time. There are 4 philosophers, and I'll put P0 there, sitting in a circle, and there are actually what look like pitchforks, but just regular forks, in between each of them. And each of those philosophers is designed to run in his own thread, and they follow the recipe that is, they think, they eat, they think, they eat, they think, they eat, and then they think again, and then they exit as a thread. That is their day. In fact, that's in their entire life, because they only live for one day. Okay? So I set this up as a global resource, because that's the way the handout deals with it. I will emphasize again that the way I'm writing this is shorthand. All I'm really saying here is this is a gesture to the fact that I have 5 global semaphores and an array of length 5 that are all initialized to 1. There really are some semaphore new calls that are involved to build that thing up, but I don't want to focus on that other than just mentioning it. Each one of those 1s basically represents the availability of a resource. If I call this fork 0, and this is fork 1 and fork 2 and fork 3 and fork 4, when this particular semaphore is locked up in this synchronized manner at a 1, I know that this particular fork is available. And that is of interest to philosopher 1 and philosopher 2, because both of those have to contend for that fork in order to pass into the eating phase of the thread. Okay? So without concerning ourselves with the deadlock scenario that was outlined last time, this is basically the thread I want them to follow. Each philosopher knows their subscript or their ID number, and that influences which forks they grab or they try to grab. And so, where did if come from? For int I is equal to 0, I less than 3, I plus plus. I want each philosopher to grab fork to the right, fork to the left. That grabbing happens via 2 semaphore wait calls against forks of ID. I messed that up last time, I wrote I. Forks of ID, and then forks of ID plus 1, but we want to mod it by 5, just so it wraps around. And let's, there we go, there. Okay, and as long as they pass through those and return from those 2 semaphore wait calls in sequence, they're allowed to eat. This is after they think for a while. Okay. After that happens, after they eat for a while, they semaphore signal these things. I don't really care about the order in which they free them. It doesn't really impact execution in any interesting way. Forks of ID plus 1 mod 5 ends that. And that is more or less what they do. There's an isolated think after the last meal, and then they return. And I did my little choreography last time where, in principle, because each of these 5 threads may be running in round-robin fashion, they probably will be, each one might get to the point where they grab the right fork. They're enough through this call that they've effectively acquired the fork because the 1 has gone down to the 0, but they get swapped out sometime between the actual demotion there and the time they actually demote the 1 to a 0 inside. Does that make sense? So it's possible. I don't want to say it's unlikely. It's actually, it's actually unlikely unless you force it to happen. But actually, I don't want to say that. Because it's possible, it's a problem. If all 5 threads could be swapped out right here and all be experiencing mutual deadlock because they're all depending on the philosopher to his or her left to be releasing the fork that is their right but your left fork. Okay? Does that make sense? Normally what you do, put all your semicolons in, but normally what you do is you implant the minimum amount of work to remove the possibility of deadlock. We made some observations in the final 10 minutes of lecture on Monday, or Wednesday rather, where we know, because of 5 div 2 is 2, that at most 4 forks can be held while philosophers are eating. Okay? So we could recognize that there are at most 2 philosophers going to be able to eat at any one time. So we could actually put something of a generalized counter right there and right there, and actually force each philosopher to become one of the blessed 2 that's allowed to go ahead and grab forks. Does that make sense to people? Okay. So what I did is I did this semaphore, a single semaphore, num allowed to eat. And I could initialize it to 2. Let me get rid of these arrows. And I could sneak in a call right here where I say, please wait for me to be one of the 2 that is allowed to eat. Okay? It's something of a critical region. It's not the same type of critical region we saw before. Critical region normally means at most 1 because there are concurrency, there are race condition possibilities. This is a different type of critical region. In fact, most people wouldn't call it a critical region, but I'll call it that. But we only want 2 threads to be somewhere between here and this part right here. Okay? Because if we have any more than that, then we're nearing the scenario where we might have deadlock. Okay? Does that make sense to people? So let them go ahead, grab forks, eat, release the 2 forks, and when they're done, saying basically I have left the table, so that means I should signal all the other threads or all the other philosophers that might be waiting for permission to grab forks and do a final semaphore signal call right there. Okay? Does that make sense? Now if you put 2 there, I would completely understand why you did that. I personally, even though I recognize that there are at most 2 threads allowed to be in here, okay, or the way we've actually programmed it up, that at most 2 philosophers will really be calling the eat function. My preference, just because I'm a purist about it, is that this be a 4 instead. Okay, now a really terrible value would be 5. If I have 5 philosophers, then basically the semaphore wait is just this gratuitous semaphore that everyone has to consume, but there will always be 1 there. The reason the 4 works is because as long as somebody's prevented from grabbing either fork, then there's at least 1 philosopher thread that's capable of grabbing 2 forks. Maybe the other 3 are blocked, okay, but it's always the case that at least 1 philosopher will be able to grab 2 forks. That makes sense to people? That's the minimum amount of of a fix that I need to implant into the code to make sure I don't have deadlock. So concurrency and multi-threading purists usually like to do the minimum amount of work to prevent deadlock. There's a reason for that, because the minimum amount that you implant there, you remove the deadlock, but you still grant the thread manager as much flexibility in how they schedule threads as possible, okay? When I put a 2 there, I'm taking more control over how threads are scheduled. That means up to 3 threads can block on this line right here as opposed to just 1. Does that make sense? Okay. If you make this a 4, that means that up to 4 threads can make as much progress as is really possible before they're blocked and pulled off the processor. Whereas if I make it a 2, we're blunting some threads prematurely. Okay. Does that make sense? Okay. So that's what I like about that, and this is why I prefer the 4. If you put 2, 3, or 4 there, it will be programmatically correct. If you put 2 or 4 there, I think it'd be correct from a design standpoint. I prefer the 4. Yep.
Maybe this is a dumb question, but why would we use a semaphore as opposed to like an if statement on like a global variable? Is there any really good reason to?
We could. In fact, I'm going to talk about that specifically. You could, rather than doing this, where you actually have the integer. Basically, this tracks a resource. I like to think of this as the number of shopping carts that are available in front of Safeway. Okay, and if there are 5 people that approach the store and it's a requirement that all of them have a shopping cart, they all flash mob the 4 shopping carts, but only 4 walk away with 1. So 1 is blocked until at least 1 shopping cart comes out the exit door. Does that make sense? I could, and I think this is actually a really good question, so pay attention to my beautiful answer here, that I could have just put a global integer here and set it equal to 4. I could have had this check to see whether or not it was greater than 0, and if so, acted on it. But then I have the separation between test and action that was problematic in the ticket agents example. Does that make sense? Well, you could solve that by having an exposed global integer and a binary lock like we did for the ticket agents example. But then what happens, and you have to think about this, I don't really want to write any code because I don't think I have to. Rather than just blocking on the semaphore and letting the thread manager decide when you can get the processor back, what you'd have to do is you'd have to do some little while loop, okay, around and repeatedly check to see whether or not the global variable went positive from 0 if you were blocked on it. Does that make sense? You'd have to keep acquiring the lock and releasing it, acquiring the lock and releasing it, because you can't check that variable unless you actually are the only one looking at it. I'm losing my train of thought here. Where'd I go? The problem with that, from a programmatic standpoint, and this is, I think, is a pretty good point, is that if you're basically while looping, you really aren't allowed to do anything meaningful until you get beyond the while loop. So what's going to happen is you're going to be hogging the processor. Maybe in the same time slice, you're going to just keep reacquiring and releasing the lock just to confirm that it's still 0. Does that make sense? That's what's called busy waiting. There are some scenarios where busy waiting is actually fine. It usually is in the case where you have multiple processors and you expect some other thread running on another processor to release a resource pretty quickly. But in a single processor environment, which is what we're pretending we have, there's no reason for a thread to spin lock and keep checking the value of a global variable because it's not going to change until somebody else gets it. Does that make sense? So this right here is this very clean way to say, you know what, I'm not making progress, let the thread manager pull me off, put me on the blocked queue. Only when someone signals the semaphore that I'm blocked on will the thread that's blocked on this thing ever be considered for the processor. The alternative is to use the global, exposed global with a binary lock, programmatically correct, but it encourages busy waiting, and busy waiting is like probably the, I don't want to say the worst thing. The worst thing is having a race condition exposed. But it's, as far as correct coding is concerned, it's the least good in terms of design because it wastes processor time. That could otherwise be shared to the people to the threads that really can get the work done. Okay, does that make sense? 2-second question, 4-minute answer. Okay, you guys are good with this right here? Okay, there's that. I want to start talking about a couple other things. I have 2 related examples. One I'll actually write code for, and then another one I'll just talk about the design. I want to start thinking about more practical problems. I'm going to frame the next example in terms of just FTP downloads. Okay, I know FTP is kind of this 1990s technology, but we all still use it. Okay, we actually go and fetch files. We actually use programs that use FTP. But let me just assume the existence of this function. I have this function, int, I'll call it download single file. And what I'll do is I will give it two things. I'll give it a const parstar. I'll call it a server. And I'll give it a second name called path. I know you know what this means. Server is basically the computer that's hosting the file that you're trying to get. And path is basically relative to where the web directory or the FTP server is behind the scenes, how to get to the particular file of interest. Okay? So this is basically the computer it lives on, and this is effectively the file name with directory